This node represents the acceleration vector, a, which measures how quickly the capsule's velocity is changing. In the context of our terminal velocity derivation, we are specifically looking for the moment when this vector becomes zero, meaning the forces of gravity and drag have perfectly balanced out. Would you like to see the next step of the proof where we apply Newton's second law to these forces? This node represents the equality operator in Newton's second law, F net equals ma. It serves as the physical bridge between the forces acting on the capsule, gravity and drag, and the resulting motion. In our terminal velocity derivation, this is the most important step because it tells us that if the capsule... This step identifies gravity as the primary force pulling the capsule toward the ocean. Mathematically, we express this weight as Fg equals mg, where m is the capsule's mass and g is the acceleration due to gravity, approximately 9.81 meters per second squared. In the 3D scene, can you identify which colored vector represents this downward gravitational force? This node is the drag equation, which calculates the aerodynamic resistance force, Fd, acting upward on the capsule and its parachutes. It shows that drag isn't constant. It depends heavily on the air density, ρ, the size of the parachute, a, and most importantly, the square of the velocity, v squared. Because drag increases so rapidly as the capsule speeds up, it eventually grows large enough to perfectly cancel out the weight of the capsule. Would you like to move to the next proof step to see what happens when these forces balance? This node represents the core physical product that determines the magnitude of aerodynamic resistance. It combines the atmospheric density, ρ, the square of the velocity, v squared, and the effectiveness of the parachute, the product of area, a, and drag coefficient, cd. In our terminal velocity derivation, this product is the engine of the drag force. As the capsule falls faster, this entire term grows until it is large enough to counter the capsule's weight. Would you like to move to the next proof step to see how we set this equal to gravity to find the terminal speed? This node represents the equilibrium point, where the downward pull of gravity and the upward push of drag are perfectly balanced. Think of it like a tug of war ending in a tie. Because the forces are equal and opposite, the net force is zero, and the capsule stops accelerating. This specific balance is the physical definition of terminal velocity. Would you like to see the next step, where we substitute the full formulas to begin solving for that velocity? This node represents the master equation for terminal velocity. We have substituted the specific formulas for weight, mg, and drag, 1/2 ρ vt squared cdA, into the balance condition, where Fg equals Fd. From here, the physics is complete, and we simply use algebra to isolate Vt and find the final speed. Would you like to proceed to the next step of the derivation? This algebraic step simplifies the equation by removing the fraction. By multiplying both sides by 2, we transform mg equals 1/2 ρ vt squared cdA into 2 mg equals ρ vt squared cdA, making it much easier to isolate the terminal velocity vt in the following steps. Would you like to move to the next step to see how we isolate VT squared? In this step, we use algebra to get VT squared alone by dividing both sides of the equation by the density and drag terms, rho CD A. Physically, notice that the parachute area, A, is now in the denominator. This confirms our intuition that a larger parachute, larger A, results in a smaller terminal velocity. We are now just one square root away from the final formula. Would you like to finish the derivation and see the final formula for terminal velocity? This is the final result. The formula for terminal velocity, Vt, equals the square root of 2mg over rho CdA. Taking the square root of both sides isolates the speed itself, giving us a precise way to calculate how fast the capsule will be moving at splashdown. The formula reveals the fundamental trade-offs in landing physics. Mass, m, a heavier capsule falls faster. The drag coefficient, CD, is a dimensionless number that describes how aerodynamic an object is. A low CD means the shape slices through the air easily, like a needle, while a high CD means it is very draggy, like a parachute or a blunt capsule. In our semantic graph, this node has an outgoing connection to a multiplication operator at multiplication, where